Good afternoon, everybody. Welcome back to a new lecture on information retrieval. We are going to finish today this part on tolerant retrieval. I still owe you the edit distance. Then we'll look into the Jaccard coefficients, and finally into how to spell check based on sounds, on how words actually sound. But before we do that, I would like to ask you a few questions, 2 or 3, I think, on the Clicker app, and then we'll be ready to go. So I have questions for you on B+ trees. So this is the first one. I'm giving you 4 structures, and I'm asking which of the following data structures are a 3-5 B+ tree, knowing that we follow the conventions of the lecture, because I gave you the warning. If you tried to go to the internet and Google your way into B+ trees, you will find that there are many, many different conventions, right? So I'm using the conventions that we established last week. So these are the first 2 trees that you can see right here on the screen. Of course, I'm assuming you can see them on your smartphones and on your browser as well. And these are the other 2. We have 17 answers so far, 20 people on Zoom. How many people in the lecture hall then?
I'd say around 15.
15? All right, 35 in total. All right, 19. Okay, let me stop here. Let's see what you did. So, aha, very, very interesting. So the majority is not correct. So that's very interesting. So let's have the discussion. Let's start with the first one. Can anybody tell me why the first answer is not a 3-5 B+ tree? We have a hand microphone in the lecture hall, and you can raise your hand if you're on Zoom, or you can also write on the Zoom chat if you prefer.
Chat that says length 5 is not allowed.
Exactly, that's exactly it. So you see here, you have 1, 2, 3, 4, 5. But then you may think, okay, that's a 3-5 B+ tree, so I can go all the way to 5. Yes, but no, because 5 is the maximum number of children. But we saw that if the maximum number of children is 5 for a node, it means the maximum number of keys is 4, right? Because if there are 5 trees, there are 4 intervals. So 3-5 B+ tree means that the number of children is between 3 and 5, but the number of keys in the same node is between 2 and 4. So this disqualifies the first one. There is a second reason that was not intentional, but here it's supposed to be a 22 and it's a 2. So of course that wouldn't be sorted. That would be a second reason why it's not a B+ tree. But anyway, let's go to the third one. What is that? Why is that not a B+ tree?
I'll let you answer. We have an answer here in the hall.
Mm-hmm.
This is a B tree?
Yes, absolutely. Is it a 3-5 B tree?
Wait, 1, 2, 3, 1. Yes, I think so.
Yeah, absolutely. Great. So great answer. Indeed, this is a 3-5 B tree, and that doesn't qualify as a B+ tree. The B+ tree only has the actual the actual terms of the standard inverted index on the leaves, right? But here you see that it's all over the place. It's at all the nodes. I have only one color in here. So this is why it's a B tree and not a B+ tree. What's good? Yeah. Go ahead.
An answer in chat, it says it's also not sorted.
And it's also not sorted. Yeah, that's true. There's the 13, 4, 15. That would be another reason. So in that case, yeah, I think the 1 is probably missing. There's a formatting issue here. So actually, the 4 would disqualify it even as a B tree. Actually, the fact that it's not sorted. You're absolutely right. Okay, and the last one. What's going on with the last one? Why is that not a B plus tree?
The leaves are not on the same level. Answer from chat.
Yep, exactly. In a B plus tree, all leaves must be at the same level of depth. And indeed, here we have depth 1 and depth 2, so that's not okay. All right, and here we have a 3, 5 B plus tree. But wait, the root only has one key here. And we said that 3, 5 means that there should be between 2 and 4 keys. So why is that a 3, 5 B plus 3? Anybody?
Not in class and not in chat.
Okay, then you might remember that the rule of the minimum does not apply to the root. That's the exception in a B plus tree. So even though it's between 2 and 4, that applies everywhere, but for the roots, it's fine if it's less than 2. It's still the maximum must be 4, but the roots can absolutely have less than the minimum. It's the only exception in the entire tree, and this is why it is a B plus tree. And it's also nicely sorted, and there's not even any 1 missing in the numbers. Okay, so that was the first question. Let me give you another one. We are considering now 4, 7 B plus 3s, hypothetically, right? So that would be, technically it's not D plus 1 to D plus 1, but nevertheless, you could consider B plus 3s between 4 and 7 children, right? So if a B plus 3 can have between 4 and 7 children, how many terms, so these are at the leaves, the keys on the leaves, how many terms can a 4, 7 B plus 3 of depth 3 contain at most? And with the depth here, we mean that if you have just the roots, that would be depth 0. And then if you add 1 level, that depth 1, and so on and so on. You could also, I think an alternate name is the height, with the height of 3. Some people call it. So here, of course, you can use a calculator if you want. So remember, depth 3 means there's the roots, then there's the first level of nodes, then there's the second level of nodes, and then the third level, that's the leaves. How many terms at most? How much can you fit in there? Let me start looking at your answers. 2,401. So how do you go about it? Can anybody explain how you compute this? Then we'll see if the majority is correct. Does anybody have a reasoning? In Zoom, you can raise your hand in the lecture hall. You can write on Mattermost if you prefer.
We have an answer here in class.
Yeah.
Just a second. It's on.
It's 7 to the 4th power because there's the 0, 1, 2, and 3 levels, and each time we can multiply by 7 for the number of entries.
Okay, so you say 7 times 7 times 7 times 7, right?
Yeah.
And this is how you obtain so you obtain 2,401 this way, right?
Yeah.
Okay,
Yes.
and so the majority says this. Does anybody have another opinion or would like to defend a counter opinion? So anybody who answered 2058? Do we have anybody who answered 2058 and who would like to explain? So let me give you a bit of courage. That's actually the correct answer. Go ahead, I'm listening.
Okay, we have someone here in the class.
Mm-hmm.
Okay. I calculated 7 to the power of 3 and then times 6 because there's only 6, like the maximum number of children or items is 6, not 7.
Absolutely, absolutely. And this is correct. So indeed, you needed to remember for this that 7 is the maximum number of children, but what we are counting is the number of terms. So we have 7 times 7 times 7 leaves in the tree, but on every leaf, there are not 7, but there are 6 different terms in there. So this is why the last one is a times 6. Does it make sense to everybody? Right, so congratulations to those who found this answer. And for those who did 7 to the power of 4, then that again, I can say again, because somebody told me at the end of last week that I should say it again. So I encourage you to make mistakes. Make mistakes all you want. You are students, you are studying, you are taking lectures, taking exams, you're learning. So you're just here to make mistakes. And the more mistakes you make, the more you learn. A great way also to learn is to try to explain to other people. If you talk together and explain to each other how things work, then that's a great way to see when you start seeing that you're not able to explain something, then that points you to what you can learn a bit more, right? So really be never afraid to make mistakes. You can give all the wrong answers you want in this course. You're completely safe with us, all right? So, okay. Let me now get back to the slides. And by the way, I make mistakes all the time too. I'm also learning and learning and learning. Okay. So where were we? We were at the spelling correction. So how do we approach spelling errors? So these are the last few slides of last week. So this is something you already saw, right? So what happens is that we can look for the corrected terms, only query terms, only query for corrected terms if they are not in the dictionary, or also if we don't have enough results, or the super conservative solution is to just make a suggestion, right? And so I give you this example. So we want to see how close two words are, because what is a spelling mistake? It's when you have a word that is not in the dictionary, but that is very close to a word that is in the dictionary, right? Because you just make a spelling, and by the way, yeah, make mistakes, also spelling mistakes. I didn't notice the coincidence, but yeah. So when you have a spelling mistakes, you're just looking for the closest word in the dictionary to what you wrote. And the question is, what do we mean with close? And one of the ways to define close is to say how many edit steps do we need from one word to the other. So here I took two words that are just 2 letters and 2 letters, right? Of course, you can generalize to any number. And what we notice here is that in that case, I'm going from or to to. So what I'm doing is that I'm removing the R and then I'm adding the T. So that's 2 steps, right? Another way in 2 steps is to replace the O with a T and to replace the R with an O. So we can delete, we can add, and we can replace. That's the 3 things that we can do. And so the minimum edit distance is to find out what's the minimum number of steps that you can apply from here to here, right? So we saw that in these cases, typically, you can go for the brute force approach. The brute force approach means you try to find all of the possible ways that you can go from one word to the other. So I showed you last time that it's exponentially exploding all the combinations. So you need to scratch your head a little bit in order to get the structure of the tree, but this is not what's important, the structure here. What's important is that if you try to consider all of the ways you can go from one way to the other, like this is one of them, this is an exponential explosion. And you know, we're computer scientists. We do not like exponential explosion because that's just not something that is tractable computationally, right? So we don't like that. However, so we can, of course, we could try a depth first search and a breadth first search, but again, in an exponential growing tree complexity, that's just not okay. But there is a trick that I told you about. It's to notice that if you look at this gigantic search space, you will notice that a lot of nodes are exactly the same. Here, you know, this is how we go from O to T. So we are at some point of the way between O and 2 here, and we are looking at the difference between O and T. But look, this here is the same thing as here. Here we are looking at the difference between T and nothing. That's the same thing as here, 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 here. So what do mathematicians do when they notice that they have a very big set and they have duplicates, they have elements that they can group together in the sets? They would kind of be duplicates if they would consider them equal, right? So what do? You build equivalence classes. Equivalence classes are just big bags in which you put your items. And so we are just creating a yellow equivalence class for these ones, a red equivalence class here, an orange equivalence class, a blue equivalence class. So we just put them in equivalence classes. And then we do a magic thing that's called the quotients. We take the quotients, it's magic, it just merges everything that is in the same bag into a single item. And what we end up with is this. And if you rotate it just 45 degrees, what you get is a rectangle. And what that means is that instead of exploring the entire search space, you can explore the quotient of the search space by the equivalence relation. But it turns out that this is quadratic. It's no longer exponential. And this, ladies and gentlemen, is called dynamic programming. Dynamic programming is exactly this. You take the quotient of an exponentially sized search space that you're too lazy to explore, and you turn it into something quadratic, and then you just fill it line by line like this, right? So in every place here, we consider the distance between the prefixes of the two words that we consider. All right, can we directly build this? And the answer is yes, we are going to use dynamic programming to do this in quadratic complexity. So I'm taking another example, 3 letters, 3 letters. I'm going from cat to 8, right? So how do we do this? Every cell here has the distance between the prefixes. For example, here, this number that we will put here is the distance between CA to go to A. What we will put here is the distance to go from C to 80, right? And we just go line by line, and we are of course going to be smart because we are going to use recursion. That's the beauty of dynamic programming. So we start here. What's the number of edit steps to go from the empty world to the empty world? It's also called epsilon in theoretical computer science, in the monoid structures, if you want to sound smart. So the distance is 0 because it's empty. You want to go to empty, so you have nothing to do. It's still empty, right? So the distance is 0. Now, these are easy to fill. If you go from an empty world to a world, then you just need to add A. Here you add A and T, and here you add AT. Starting from nothing. Going from C to the empty world, you just remove C. Here, CA to the empty world, you remove C and A, that's 2 steps. And here, CAT to the empty world, you remove CA and T, that's 3 steps. Okay, so these are the easy ones to fill. And now we are just recursively going row by row. So let's try to put something in there. We would like to find the minimum distance between C and A. How do we recursively find that? Well, we are going to be lazy and look at bringing it back to a problem we already solved. Can we express the distance between C and A from the distance between C and nothing, nothing and nothing, and nothing and A? Well, let's just consider the delta. What if we know how to go from C to nothing? Can we go from C to A? Yes, absolutely. We first go from C to nothing, and then we add A. Right? That would be 1 + 1, 2. Or if we use this step instead, we know how to go from nothing to nothing. How do we go from C to A? Well, we can go from nothing to nothing and then substitute the C for an A. That's one step, right? Plus 0. And here, if we know how to go from nothing to A, how do we go from C to A? Well, I just remove C, and then I'm back to that problem of going from nothing to A. So that's one step for removing C plus the one that is there. So you see, we are looking for the minimum of the three, because here it took 2 steps, here it took 1 step, and here it took 2 steps. What was the shortest? That was coming from here. That was the 1. So minimum of 2, 1, and 2. So we put a 1 in there. And then we do it again. Here, the minimum between 1 plus 1, 2 plus 1, that's 3, or 1 plus 1, the minimum of that is 2. Here, the minimum between 2 plus 1, 2 plus 1, or 3 plus 1, the minimum is 3. That came from here, right? Here, now, here something is different. Why is that difference? Because I have the same letter here and here. And the reason it's different is like this. Okay, we want to go from CA to A. Either I know how to go from A to nothing, so I removed A basically sorry, C and A to 0, and I want to go from C and A to A. So I have the 2 steps to go to nothing and a 3rd step to add A. So that gives me a 3. If I come from here, I start removing the C, that's the 1st step, and then oh no, I should have said removing A here. I remove the A, and then I know how to go from C to A plus 1 step, so 1 plus 1, 2. But this is where it's different, because here I go from C to nothing. That's the problem I know how to solve. How do I go from CA to A? Well, I can just, from the C part, go to nothing. That's 1 step, and A replaced with A. But A replaced with A is not really an edit. That's 0, right? So if the letter here is the same as the letter here, what you do is copy just that number over there, right? So it's 2 plus 1, that's 3. 1 plus 1, that's 2. 1 plus 0, because it's the same letter here and here, gives you a 1. So the minimum is 1. And you just continue filling the table like this. And now you have the distance between cat and 8. That's a distance of 2. And you can even add, if you keep track of where the mean comes from, and you actually build the table also keeping the pointers, then you can even remember where what was the path that you used to get that minimum distance of 2, right? So in that case, you have 8 that came from transforming cat to at. Here that came from at, here, at, and cat. So cat, at, that's 0. You see 1, 1, 1, the distance doesn't change. Cat, at, 8, right? So what we did is remove the C here, and we added back the E here, right? These are the 2 steps that we have. So you see, with dynamic programming, we just managed to solve that in quadratic complexity, right? That's the trick. All right. Any questions on dynamic programming and on computing the edit distance? Is it clear to you? I can give you 2 words, you can compute it, right? Okay. So now, so you're supposed to know how to do that, right? To compute edit distances, and I encourage you to train to your dynamic programming skills in order to do that. Okay, here's now the problem with the raw edit distance. We need to compute that distance when we want to spell check a word. We don't know which word is the correct one. So we technically would need to compute the edit distance against 500,000 terms. Let's imagine that's the number of terms in our collection. That's a lot of edit distances to compute, right? It's in quadratic time, but still that's 500,000 times computation, right? So it's a lot, and then we'll take the shortest edit distance, and that will give us the most obvious correction to the spell check, right? Okay. So it's just not feasible in practice. You cannot every time compute 500,000 edit distances. I mean, you can guess that if this is what Google were doing, you wouldn't get the did you mean notice in such a short amount of time. Right? All right. So in practice, we actually select just a few terms. How do we do that? Well, there is an alternative way of characterizing a closest word. Let's consider an alternate way. So edit distance is 1. Let's now look into another one. Do you remember these k-grams that I told you about? The k-grams, it's the sliding window over the letters of a word. 3 grams, for example, is just 3 letters, 3 letters, 3 letters. So we are going to assume that a small edit distance could mean that they have many k-grams in common. It means that the words would be close, right? So they would be close to each other. So what that means is that if you consider, these Venn diagrams, you have 2 sets and then you plot their elements to see the intersection, the union, and here the subtraction. So in that case, that would be 2 words that are very, very close because they have a lot of k-grams in common. And here you would have 2 words that are distant from each other because they have very little in the intersection and a lot of them not in common. Here's an example with an actual spell check, right? So here the mistake is I forgot the O, right? Computer, but I forgot to write the O. So I'm comparing it to computer, which is the correctly spelled word. So what do? I put all the 3 grams that I find in there. So remember, you need $1 here and $1 there. So that gives you $CO, COM, OMP, MPU, PUT, UTE, TER, and ER dollar, right? So you can put them here in the blue circle. Then you do the same with computer. That's $CM, CMP, MPU, PUT, TER, and ER dollar. You put them here. Now you notice that 1, 2, 3, 4, 5 are common to the 2. CM and $CM and CMP are only here, and CO, $CO, COM, and OMP are only there. So this is the actual diagram. So now we are looking at how many they have in common. 5. That's quite a good number, 5, right? Here's another example. I'm taking a word that has absolutely nothing to do with computer, a root, right? It's very unlikely, of course, that this was a mistake trying to spell computer. I wrote down root, right? So maybe with the autocorrect, that sort of things can happen. I don't know, but not if you just type on your keyboard and make a mistake type, right? But what happens if it's not technically a good correction? Well, you see there's only 1 3 gram in common. So that tells us, okay, these 2 words are far away from each other. Right? So this is very unlikely that if you type that word, you actually meant that. Very, very unlikely. So once you have that, you can look up the k-grams. So you remember this k-gram index that we built last time, right? So we took all of the words in the dictionary, we computed all of their k-grams, and we nicely arranged the k-grams in a B+3 that points to the terms that they came from, right? So we take the k-grams from this. This is what it gives us. So here k equals 3. I'm taking the 3 grams. Then I look them all up in here, and I'm going to find here that I colored them in green. So computer, 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 and Terran. So here there's also, you need, if I'm looking specifically for TER, I find this, right? So these are all the k-grams that I'm looking up, and this is what I found. So you see, I see computer a lot of times. So you see computer is probably a very good candidate. Terran may be less, because here you just have the TER in common, right? But you see the logic. I'm using this k-gram index to resolve all the k-grams in my actual mistaken query. And then I find out all the words that contain these k-grams, and then I try to find those that appear very, very often, right? So in the case of computer, I have 5 in common. You see 1, 2, 3, 4, 5. So these are the k-grams, the 3 grams they have in common. But for Terran, there is only 1. That was the TER, right? So it's very likely that if, in that case, I'm only considering 2 terms, right? But in that case, computer is the obvious candidate and not Terran, right? Why? Because it's the higher one. So we have 5 3 grams instead of 1. So we could say, okay, for example, we consider that we have a good correction where we have a threshold of 3. So we could say arbitrarily, if there's at least 3 grams in common, then we consider that that's a candidate that we keep, right? And then we can compute the edit distance on those that we have that meets the threshold of 3. What is the problem with that? If we just have this absolute threshold on the number of k-grams in common, do you see any problem? Okay, let me show you then. You just need to take longer words. If you take longer words, you see, for example, board and boardroom, you see that now there are so many k-grams that even though in relative terms, there's not so much in the intersection. We do have 3 here. So that would actually meet the absolute threshold we have here, even though in that case, that's undesirable because of course, if I type boardroom, I didn't make a mistake that I meant board, right? So that just doesn't work. And the issue here is we had an absolute number here. I was trying to put a threshold on the absolute number of k-grams that are in there. What should I do then in order to fix that, to make it relative? Some kind of renormalization, right? So when you want to make something absolute relative, you renormalize, but how do we renormalize that? What do we divide it with? Any ideas? You want to have something that expresses the total size, right? In the chat, maybe?
Divide by the total number of k-grams?
Yes, exactly. That's exactly what it is. You basically compute, okay, let me use technical terms, the cardinality of the intersection and the cardinality of the union. That's what you said in the chat correctly. That's the total number of k-grams. And we just do the division. So here it's 3 divided by, oh, there are so many, I have to count them. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 3 divided by 12 gives me a quarter. So it's 0.25, right? Now this is relative, and that's between 0 and 1. Right, 0 is the case that they are completely separate. 1 is the case that it's the same. Well, maybe not the same word, but all the k-grams are in common, right? Okay. Great. So this is called the Jaccard coefficient. Why is it not called the Jaccard distance? Because we said edit distance, right? But then I'm not calling that Jaccard distance. I'm saying Jaccard coefficient. Why not the Jaccard distance? Okay, let me just tell you. What is a distance? It's a number that when it's close to 0 or even 0, it means that 2 things are very close. 2 words, for example. The distance should be 0 if they are very close to each other. But when the Jaccard coefficient is 0, that's the opposite. The Jaccard coefficient 0 means it's completely separate. It means the 2 words have nothing to do with each other. In the case of the Jaccard coefficient, if the words are close to each other, it's close to 1, actually. It's the opposite. So this is why it's not called a distance. We cannot call it a distance. It wouldn't make any sense. So this is why we call it a coefficient. And again, the Jaccard coefficient may be close to 1 for a spell correction. For the edit distance, it must be close to 0, right? 0 meaning that it's exactly at the same place. All right. Okay. Okay, this one. What is the Jaccard coefficient here? Can anybody tell me? Between the words computer and routes.
Uh, 1 divided by 11.
Yep, exactly. 1 here, 11 in total, 1 divided by 11. Yeah. Okay, what about this one? Dan, in the chat, I think.
1 divided by 2.
Yeah, exactly. We have 5 in there, 10 in total. So that's 5 divided by 10 gives us 1. All right. So I think you get it now, right? So how you compute a Jaccard coefficient. All right. Do not forget the dollars. That's one of the common mistakes here, right? So if you compute the 3 grams, you always need to add a dollar here and the dollar there, and then you compute the sliding windows. Okay. So we could, the updated method is we get the k-grams, we look them up in the k-gram index, we compute the Jaccard coefficients, and we keep the terms with the large Jaccard coefficients, right? So this could be a method that we use in order to optimize. Now, the problem is we need to compute the Jaccard coefficient, and we need to do that for still a lot of words, maybe not 500,000, right? But at least for all the words that we found in the K-gram index. Can we optimize this? And the answer is actually yes, because the numbers here, they are easy to compute. First, this number right there on the top of the fraction, we already know. It's the number of K-grams that the query terms has in common with the candidate's correction. And here you just need to count the number of times you found it in the 3-gram index, right? That's just how it is. So you basically know that number. So this is the intersection. And what is the union? Well, you might know that you can compute the cardinality of the union with the cardinality of the sets and that of the intersection, right? You probably know that you can take the total number of terms on the left in the first set, plus the total number of terms in the second set, but you have counted some twice because the ones in the intersection, they're well on both sides. So you need to subtract it, right? So the cardinality of your union is cardinality of the left plus cardinality of the right minus the intersection to correct for the duplicates. But this here is the same as this. We already computed that. Right? So this we know. The total number of query terms K-grams, well, we just need to compute it once. There's only one query term. So this is very easy. And the K-grams of the found term, this is something we can compute in advance. When we build the K-gram index, we can just pre-compute that all, right? So when we are at runtime, this is basically a constant. We just look it up and that's it. So you see, just with that number, I can very efficiently compute that Jaccard coefficient. Example, computer, I take the 3 grams, I look up each one of the 3 grams in my 3-gram index. I see 1, 2, 3, 4, 5 times the word computer, right? If I take computer, for example, and now I compute the Jaccard coefficient between computer and computer. How do I do that? Well, remember that we found it 5 times there. So the distance, the coefficient, Jaccard coefficient, the 5 goes here. The 5 goes there as well. I told you, this is the total number in the query term, the computer. This is computer. This was pre-computed as part of the index. And again, 7 plus 8 minus the 5 that are on both sides, right? So this gives us 5 out of 10, 1/2, right? And that's the solution we found earlier as well. So you see, this is correct. Okay. Now, in practice, people still love edit distances. So what they do is that they do something hybrid. They basically still use the K-gram index in order to just restrict to just the terms that you found via the K-gram index. But after doing that, they drop the K-grams. They just switch back to the edit distance and then compute the edit distance, but not for the entire dictionary, only for the terms that you found in the K-gram index. So this is how, in practice, many people do it. All right. Okay, this is the end of the K-gram indices, the Jaccard coefficients. Now here's another way that you can spell check with the context. For example, if you say graduate from form ETH, so that's a mistake, that's an on-purpose mistake because I want to illustrate something. So graduate from ETH. Here, the problem is that that word actually exists form, but you can still see graduate, graduated, graduation, from, form, ETH, etc, ETH. So these are possible checks, right? But if you look up into the bywords from potentially other users, you basically look at what word is next to another word. Graduate is likely to be followed by from. Graduate from is a byword that you find in many places. From ETH is also something you find at many places. Graduate form and form ETH, rather unlikely, right? So you can actually, with the context, and now it's by words, it's still sliding windows, but on words, we can actually also use the bywords index in order to do some context-sensitive spelling correction. All right. Any questions before I move on with the last thing I want to show you in the spelling correction? Any questions? No questions? Everybody understands everything that I'm telling you? All right, then I'm assuming everybody understands everything. Again, never be afraid to ask questions. Never be afraid to make mistakes, and never be afraid to ask questions. Okay. Oh, do we have one?
How would we choose K for K-grams?
Good question. So here, I think it's kind of trial and error, right? So the rule of thumb that I gave you is that probably 1 grams are useless. Probably 5 grams and more are too complex, right? You would have a very few words for every 5 grams. So typically 2, 3, and 4 are kind of the sweet spots where we look at, right? You can do 2 grams, 3 grams, and 4 grams. And then it's really just a matter of performance, the distribution of the words. It's really trial and error, right? So it's always a compromise that you make. If you look at 2 grams, 2 grams, bigrams actually, is going to be smaller, the bigram index, because there's less combinations, right? It's just 26 times 26, if you only consider letters. So the index is going to be much smaller, right? So it's all faster and faster and faster. The problem is that you might have a lot of false positives, right? You might have a lot of collisions and you don't have enough information in there. If you go to 3 grams or 4 grams, then of course the index is going to be larger. It takes up more space. It's a bit slower to execute, but you will start getting more precision in the way that you resolve the words, right? Did I answer your question? Okay, wonderful. Okay, now let me switch to phonetic correction. That's a beautiful algorithm that basically looks for, again, a word that is similar to the word that you didn't spell correctly, but only based on how it sounds. And the way it works, it's called the SoundX algorithm. It's designed for English. By the way, it will not work in another language, or maybe you need to adapt it to other languages. The idea is that every single word can be reduced or hashed or whatever you want to call it to a fingerprint of 4 characters. Right. Here's how it works. I'm taking here 6 words, and I'm going to convert each one of these words to that fingerprint, right? To the SoundX fingerprint. All right. So how do I start? Well, these are my words. The first thing is that I have this lookup table. It's always the same. There's only one. That's the lookup table, right? The lookup table with big V, big L, and big T, and you know there's only one. So when you have A, E, H, I, O, U, so all the vowels you recognize here, that maps to 0. B, F, B, B, so these are the fricatives. I think it's called map to 1. S, K, J, K, K. So you see, it's the one that are a bit more in the back. That's 2. D, T, that's the dentals, map to 3. L, map to 4. M, N, that's the nasal ones, map to 5. And R, well, here it depends if you're in which kind of English you speak, if it's more like British English or it's American English. But anyway, R maps to 6, right? So these are the buckets. By the way, these are equivalence classes. It might not have escaped you, right? But again, what do we do with that? Well, we are going to replace the letters with the numbers, except the first letter. The first letter we don't touch, all right? So let's do it. I keep the first letters, but all the other letters, I replace them. So you see that was a vowel, so that's an O, M, that's a 5, P, that's a 1, and so on and so on, right? So I just replace with digits, right? So I have always one letter and then digits. The second step, I remove duplicates. When do I have duplicates? When I have a repetition. For example, here, 3, 3, I just squeeze it to just 1, 3. I don't know if that ever happens at any other place here, so maybe that's the only example, but basically you squeeze. Because technically letter, the pronunciation, if there's double T or just 1 T, is the same. And again, that's not true in all languages. In Schweizerdeutsch, for example, if you double the T when you write it, at least in some of the spellings, then that's different because it's a T versus T, right? So it's not the same thing. But in English, it's kind of, we put it in the same bucket, right? So this is why we remove the duplicate. Then what do? We remove the zeros. They just go away. All the vowels and so on, we just ignore them. So of course, then you can ask, okay, why didn't we remove them in the first place? Well, this is in order to avoid eliminating 2. I don't have any example here. You might have a T and an A and a T, right? And you still want to preserve the T and the T, but the A prevents you from merging the 2 T's, right? Okay. So this is why I remove the zeros only after I have eliminated duplicates. And then what do? I said it's a 4-character fingerprints. I trim and I pad. What that means, if there's more than 4, then I just cut it. And if there's less, then I just add zeros, right? And now I have my fingerprints. And what you do then is you build an index with that. And when you have the query, you compute for the query the soundex, and then you look it up in the index, in the B+3 or whatever you have, and then you will find all of the words in the dictionary that sound the same. And sounds the same mean they have the same fingerprint, right? So you basically put all of your words in equivalence classes where an equivalence class sounds the same. All right, so this is what we did today, spelling, k-grams, and so on. So this is chapter 3, dictionaries and tolerant retrieval. Please read the chapter again. It's very close to the lecture. It's a new angle. And that's it. We are done with this part of the lecture. It turns out that it's also the time for the break. You probably heard the bell ring. So I will see you in 15 minutes. And in 15 minutes, we'll build super large scale indices for huge collections of books. All right, so see you in 15 minutes. Thank you.